All right, y'all, in this video, we are going to look at sections 3.3 and 3.4. So in the last video, we talked about how to find absolute maximum minimum. Today, we're going to look at more of the idea of local maxes and minimums and then what other characteristics are needed using first and second derivatives in graphing. So a lot of note taking here. So like I said, I'm not going to spend a lot of time. I'm going to kind of read through it and talk through it. But if you need to pause the video to write some stuff down, go for it. All right, so when you have a function, there's a lot of things that just the first derivative can tell us besides just the tangent lines and stuff that we've done in the past. So first thing they can tell us is that whether or not a function is increasing or decreasing. We kind of saw this earlier in chapter 2, but now we're going to make it a little bit more official. The way that you can tell if a function is increasing or decreasing is to look at the first derivative and see whether or not it is positive or negative. If the first derivative is positive on some interval, then we say that the original function is increasing, versus if the first derivative is negative on a different interval or some other interval, then on that interval we can say that the original function is decreasing. Not only can we use this for increasing and decreasing, but after you do that, that then develops what we call the first derivative test. So what the first derivative test says is that suppose you have a critical number, as we did in the previous video. If the derivative changes from positive to negative, which means based on the definition above, that changes from increasing to decreasing, then we can say that you have a local maximum. That kind of makes sense because if you think about it, if you're going up and then back down, that point at the top is considered a local max. Now, it may be an absolute max. We're not going to check that in this section. We did that in the previous section. Going the other direction, if your first derivative changes from negative to positive, which means that it's changing from decreasing to increasing, then you have a local minimum. Kind of the same idea as that if you're going down and then back up, that low point is considered a local minimum. Now, I think there's at least one example I threw in this section so you could see it, that there is a time that your derivative will either be positive on both sides of the critical number or negative on both sides of the critical number. That just simply means that at least at that point, there is not a local max or min. There may be one somewhere else, but just not at that particular critical number. So you can look at the four charts down at the bottom. They show the examples. The first one, what's it look like when you have a local max? You see it's increasing then decreasing. When you have a local minimum, you are decreasing and then increasing, and then showing you a couple examples of where you may be increasing and then stop and then increase again, or the same idea with decreasing. Those last two, you would not have a local max or min. This point right here is called something else that we're going to get into in just a second. Maybe some of y'all already know what it is, but we'll talk about that in a few minutes. So let's look at an example. If I give you a function, can you find the intervals of increasing and decreasing and then any local extrema, which extrema just means maximums and minimums. All right, so since all of this information has to do with the first derivative, the first thing I'm going to do is actually find the first derivative. So f prime of x is going to be 4x cubed minus 4x, and since I need the critical numbers for all three of these, I'm now going to set this equal to 0 and solve. I could factor a 4x out of both terms, which leaves an x squared minus 1 left over. Then I can set both of those equal to 0. So 4x is going to equal 0, and x squared minus 1 is going to equal 0. The first one's not too bad, just divide both sides by 4, so you get x equals 0. The second one, if you add the 1 over, that's x squared equals 1. And then if you take the square root of both sides, as we saw a lot in the last video, don't forget to make that plus and minus 1. Now there's many ways that you can do this, and we actually saw this back in chapter 2 when we did the speeding up and slowing down problems. But one way that I prefer to check increasing and decreasing is to actually do it with a number line. So I'm going to draw a number line, and I'm going to plot all of my critical numbers in order. So -1, 0, and 1. And I'm going to pick numbers inside of each interval. So a number less than -1, I'm going to pick -2. Between the -1 and 0, How about negative 1/2? And then I'll mirror this on the other side. 1/2 and 2. I'm going to take all 4 of those, what I call test values, and you're going to plug them into the first derivative. And we don't care whether or not we don't care what the number is. We only care about whether it is positive or negative. So if you need to use your calculator, go right for it. But if you plug -2 into the first derivative, looks like you're going to get, let's see, a negative number times a positive. So that should be negative. I'll just put a minus for that. If you plug negative 1/2 in, looks like you're going to get a negative number on the 4x. And then if you square it minus 1, that's going to be a negative number as well. A negative times a negative is a positive. And then really quickly, if you plug 1/2 in, you should get overall a negative number. And if you plug in 2, you should get a positive number. So you can now answer your first question. What are the intervals of increasing and decreasing? So the intervals with the plus signs, those are your intervals of increasing. So that would be between -1 and 0, union, and then also from 1 to infinity. The interval of decreasing would be the first and the third one. So that looks like it's going to be from -infinity to -1, union 0 to 1. So that's the first two things. That's how you find the intervals of increasing and decreasing. Then if you want to do local extrema, so what it's asking you is, where are the local maximums and also where are the local mins? So remember the definition, starting with local max. Anytime you change from increasing to decreasing, so for the first time through this, I'll put a little note above it. If you're going to go from increasing to decreasing, it looks like that occurs only at x equals 0. So at 0, you go from increasing to decreasing. So our x value is going to be 0 of the point. And to find the y value, you will plug that 0 back into the original function, which should give you a value of 3. Now for the local min, it's just backwards. Find the points where it changes from decreasing to increasing. Well, that's going to happen actually at -1 and +1. So you actually have 2 local minimums here. One of them has an x value of -1. One of them has an x value of +1. That's the x values. To find the y's, plug those 2 numbers back into the original function. So when you do that, you actually get the exact same number on both of them, and it looks like you're going to get a 2 on both of these when you do that. So that is your third and fourth answer. You have 1 local maximum and you have 2 local minimums. But that is what the first derivative helps us find. Let's do a second one for your notes. Like I said, I hate to just do one and leave you hanging, so let's do the same thing again. And like I said, if you want to pause the video and try it yourself and then unpause it, go for it. But example number 2, find the intervals once again of increasing and decreasing and then any local extrema that exist. So I'm going to work this the exact same way. I'm not going to change any of my steps. So step number 1, I'm going to find the first derivative, which is equal to 6x squared minus 18x plus 12, and to find the critical numbers of that, I'm going to set it equal to 0. All 3 of those terms share a 6 in common, so I'm going to factor a 6 out and make this x squared minus 3x plus 2 equals 0. That now factors, so you should be able to factor this into x minus 2 times x minus 1. And to get the critical numbers, we're going to set what we can equal to 0. Now remember, the 6 has no bearing on this, so don't worry about it. I'm just going to say that x minus 2 is 0, and also x minus 1 is 0. Solving both of those, the first one you should get an x equals 2. The second one you should get an x equals 1. When I draw my number line, remember, I got to figure out where is it increasing and decreasing. Please make sure you put the numbers in order, so 1 does come before 2 in this case. And then picking out some test values, I'm going to pick 0, how about 1.5, and how about 3. Plug all 3 of those numbers into, remember, the first derivative. Now you've got 3 different forms of the first derivative. It doesn't really matter. I usually stick with the last one because I'm going to do this in my head, but if you want to use your calculator, it doesn't matter which one you use. But if you plug 0 in, looks like you should get a positive number. Remember, I don't care what the number is. If you plug 1.5 in, looks like you should get a negative number. And when you plug 3 in, you should get another positive number. So now you can start to answer your questions. What is the interval of first of increasing and decreasing? So increasing is your positive intervals. That's going to be from negative infinity to 1, union 2 to infinity. And then decreasing, you're going to be just in the middle part from 1 to 2. There's your first two answers. Then you're going to find your local max and mins. So local max and local min. Remember, local max occurs when you change from increasing to decreasing. So that's going to actually be at the 1. So that's going to be x equals 1. And to find its y value, you plug that 1 back into the original equation, and it looks like you're going to get a 2. Your local min is where you change from decreasing to increasing, and that's at x equals 2. So I'm going to take 2 and plug that into the original. This number is going to get a little bit bigger, so I'm going to use a calculator real quick in front of me. So let's see. Just give me a second. You should get, actually, it's not bad at all. Wow. You get a local min of 1. Okay, I thought it was going to be a lot worse, but not too bad. So in this case, you have your intervals of increasing and decreasing. You have one local maximum and you have one local minimum. All right, so we did the first derivative, so now we got to go to the next derivative. What can the second derivative tell us about a function? So let me read through this. Like I said, if you need to pause the video to finish writing, that's fine. The definition says, if the graph of f lies above all its tangents on an interval, then it is called concave up. If the graph of f lies below all its tangents on I, it is called concave downward. Now that definition can be kind of confusing, so don't sweat too much if it doesn't make a lot of sense. Instead, here's kind of what I usually do. This is called the concavity test, and what the concavity test says is kind of like the increasing and decreasing test. If you can show me that the second derivative is positive or greater than 0 on an interval, then the original function is concave up. If the second derivative is less than 0, also known as negative on an interval, then you can say that the original function is concave downward on that interval. So to kind of show you a quick little sketch, I'm just going to try and draw a quick graph. Don't worry about it too much. But what we're going to notice is that we're going to try to find a point. And it's not going to be at the maximum minimum. It's going to be somewhere in between your max and mins. But if you look to the left of this green dot, you see that that part of the graph is opening downward toward the bottom of the page. That's the definition of concave down. Versus over here on the right, that whole piece is opening upwards towards the top of the screen, so that would be an example of concave up. Now we got to be able to find that point where they change, and that's where the next definition comes into play. We had critical numbers on the first derivative. That same idea is actually called an inflection point. So an inflection point occurs where you are changing from concave up to concave down, and this part's not in the book, but I don't know why they left it off, but this means that your second derivative either equals 0 or your second derivative does not exist. So just like critical numbers, points of inflection have the same definition as they do in the second derivative world. Now, not only can you do concavity with all this stuff, there's actually another way to find max and mins using the second derivative. And here's what it is. It's called the second derivative test. It says, suppose you have a second derivative. If you take your critical number, so remember f prime of c, this is the definition, and I'm going to call it Cn. This is the definition of a critical number. If you plug your critical number into the second derivative and it's positive, then you have a local minimum at the critical number, versus if you take the same critical number, plug it in the second derivative, if it gives you a negative value, then you have a local maximum. It seems kind of backwards, but that's the point. That's why it's not a very popular test, but I am going to show you how it works. That way, if you prefer to find your maxes and mins that way, that is fine by me. Do whatever you feel more comfortable with. All right, so before we get into the concavity stuff, in these problems, not only am I going to make you find the new inflection points and the new concavity, I'm going to verify the extrema, so the local max and min that we did on the previous problems. Let's verify those with the second derivative test. So these problems are exactly the same. So a couple things to remember. We don't need the intervals of increasing and decreasing or anything. We just need to make sure you go back and write down your critical numbers. So on this one, if you remember, you had critical numbers of -1, 0, and 1. Just kind of keep that in the back of your mind. We're going to need those in a minute. So let's start with the second derivative test. So the second derivative test says, obviously, find the second derivative. So if you want to practice again, we already did this, but the first derivative is 4x cubed minus 4x, and your second derivative now is going to be 12x squared minus 4. All the second derivative test tells you to do is to take these three critical numbers that we already found and plug them into the second derivative. So let's do that. We're going to find what is f double prime of -1, what is f double prime of 0, and what is f double prime of 1. So on all of these, just really quickly, if you need to, plug them in and see what number you get. If you plug -1 in, you should get an 8. Oops. If you plug 0 in, you get a -4. And if you plug +1 in, you get 8 again. Kind of like the increasing, decreasing test that we did. I don't really care what these numbers are. All we care about is whether or not they are bigger than 0, which means positive, or less than 0, which means negative. If they are greater than 0, which is the first and the third one, that is the definition of a local min. So if you look back to the very first problem we did, we should have found local mins to be at x equals -1 and 1. And we did, so good. The -4, since that is less than 0, remember you got to think backwards on this rule, that means that we have a local maximum at x equals 0. So if you go back in your notes a little bit, you should see that we did find a local max at x equals 0. You're not required to do it this way, but it's just a way that if you're not needing the increasing and decreasing intervals, this may save you some time, but a lot of the problems that we're going to do require you to do increasing and decreasing, so you won't see me do this test a whole lot. I'll do it one more time on the next problem, but that's about it. So now back to our new part. How about concavity and points of inflection? So let me rewrite the second derivative down here, which is 12x squared minus 4. To find your points of inflection, I'm going to set that equal to 0. So if I add the 4 over, that's going to be 12x squared equals 4. Dividing both sides by 12, 4/12 does become 1/3. And if you take the square root of both sides, you get plus or minus. The square root of 1 is 1, and root 3 just stays as root 3. All right, so this is going to look very similar to the increasing and decreasing. I check concavity the exact same way that I check increasing and decreasing. I'm going to draw another line graph. This time, though, I'm going to plot the numbers that I just found, -1 over root 3 and +1 over root 3. I'm going to once again pick test value, so how about 0? And just to make sure that it's smaller, I'm going to do -2 and +2. This time, though, since you're checking concavity, you need to plug those three test values into the second derivative. So if I remember, I don't care what they are, as long as I know whether they're a positive or negative. So starting with -2, if I plug -2 into this, you should get, looks like, a positive number. If you plug 0 in, you should get a negative number. And if you plug +2 in, you should get a positive number. And you can now answer all of your questions. You are going to be concave up on the positive intervals. That's -∞ to -1 over root 3, union 1 over root 3 to infinity, you will be concave down on the negative interval, which is the middle part. So that's negative 1 over root 3, comma 1 over root 3. So there's your first two new things you can find. All right, then you can do your points of inflection. So the definition, or in this book actually calls it an inflection point. The definition of an inflection point is any time you change from concave up to concave down. So as long as you keep alternating, every number you found over here is an inflection point. So you're going to have negative 1 over root 3 as one x value and positive 1 over root 3 as the other x value. Now these numbers are not pretty, so if you need to plug them in the calculator, that's perfectly fine. So give me a second. I didn't work this ahead of time. So if I take and we'll start with the negative one. So if I plug the negative 1 over root 3 and raise it to the fourth, and then I subtract from that 2 times the negative 1 over root 3 squared, and then I add 3 to that. Now you are going to get a fraction, but that's fine. You should get 22/9. And actually, since the original function is an even function that we talked about before, since you're plugging the exact same x value in, just one's positive and one's negative, you should get the exact same y value again. So on both of these, you get 22/9 as your y value. So a different way to find local max and mins, and then we talked about the concave up, concave down, and the idea of inflection points. Once again, I want to show you all this again because it's that important. So that second example that we did, the 2x cubed minus 9x squared plus 12x minus 3, if you go back in your notes a little bit, remember the one thing that we need are the critical numbers, and we found those to be 1 and 2. Let's verify that what we found on the second problem was correct as far as local maxes and mins go. So we need our second derivative. So f prime of x, remember, was 6x squared minus 18x plus 12. And your second derivative is now going to be 12x minus 18. Remember, the second derivative test just says you now need to take the critical numbers we found on example number 2 and plug them into the second derivative. So we're going to figure out what is f double prime of 1 and what is f double prime of 2. So if you plug 1 in, 12 times 1 minus 18 should give you a negative 6, versus if you plug 2 in, 12 times 2 minus 18 is positive 6. The numbers don't really matter. The important thing to note is that negative 6 is less than 0, and positive 6 is greater than 0. So that means when you have a negative number, you have a local maximum at that particular point. Excuse me. And if you look back in your notes, you'll see that 1 was a local max. And if you look, the positive number means you have a local minimum. And if you go back and check, x equals 2 was a local minimum in this case. All right, so once again, that's the last time I'm going to do the second derivative test. If you like that method of checking local maxes and mins, that's fine, but that's up to you. Now I'm going to do all the new stuff. So I'm going to rewrite my second derivative, which was 12x minus 18, and I'm going to set that equal to 0. Add 18 to both sides, so 12x equals 18. Divide both sides by 12, and 18 divided by 12 does simplify into 3/2. Now that's actually good news, because since you only have one number here, when you draw your number line, that is the only number you have to plot there. So picking a few test values out, how about we do 0 on the left, and 2 is bigger than 3/2, so we'll just use 2. Remember, these are getting plugged into the second derivative, and you're wondering whether or not your answer is positive or negative. So if you plug 0 in, you should get a negative 18, which is negative. We already plugged 2 in at the top, but remember, if you plug 2 in again just to make sure, you should get a positive number. Now I can say that we have an interval of concave up from, let's see, that's the positive one, that's 3/2 to infinity, and you're going to be concave down on the negative interval, which is from negative infinity to 3/2. Since it did flip-flop, that's a good thing. That means you also have inflection point. But since it only happened one time, that's because we only had one number, that means you have an inflection point at x equals 3/2, and to find that y value, plug it back into the original answer. So give me a second to plug this in. That's also giving you time to write everything down if you need to. And when you do that, hey, that's kind of funny. You actually get the exact same number. You also get 3/2 as your y value. So you have your interval of concave up, your interval of concave down, and you have your one point where the concavity switched, which is called the inflection point. All right, so what we're going to look at now is what if I just put everything together? So we haven't done a trig problem yet, so to wrap this part up right here, let's find everything. If I give you the original function, let's say sine plus cosine, and I'm going to only look between 0 and 2 pi to save you some work. Find all the intervals of increasing and decreasing, find any local maxes and mins, find all the inflection points, and then find your intervals of concavity. All right, so let's start with all of our first derivative stuff. So I'm going to find my first derivative in blue. So the derivative of sine is cosine. The derivative of cosine is negative sine, and I'm going to set that equal to 0. There's a couple different ways you can do this. I'm actually going to add the sine to both sides. So cosine of x equals sine of x. And what I notice is that if I divide both sides by cosine, that's going to give me a 1 on the left, and sine divided by cosine is tangent. So where is tangent 1? Well, there's two spots. Tangent is 1 in quadrant 1 at pi over 4 and in quadrant 3 at 5 pi over 4. So those are your two critical numbers in this interval. But those critical numbers are going to help us divide up the intervals of increasing and decreasing and also allow us to find local maxes and mins. So I'm going to plot both of those numbers on a number line. I'm going to pick out some test values. So I'm going to pick 0, 1 pi, and 2 pi, trying to make my life easy for evaluation purposes. So remember, we're going to plug those three numbers into the first derivative. That's the cosine minus the sine. So let's see what happens. Cosine of 0 is 1. Sine of 0 is 0. So 1 minus 0 is a positive number. Cosine of pi is negative 1. Sine of pi is 0. So negative 1 minus 0 is a negative number. And since technically 0 and 2 pi are on the same spot, it's going to give you the same answer, so you should get a positive answer again. So what does that tell us? That means we now can see that we have two intervals of increasing, but you can't do negative infinity. Since we're only looking at this particular interval, you have to start at that point. We're going to go from 0 to pi over 4, union from 5 pi over 4, and then you have to stop at 2 pi because of the interval. The decreasing spot is only in the middle, so that's between pi over 4 and 5 pi over 4. So that takes care of your first two answers. So you have your intervals of increasing and decreasing. And then the second part of the first derivative is, do you have any local maximums or do you have any local minimums? So the definition of a local max is when you change from increasing to decreasing. So that does occur at the pi over 4. So we will have one local max. And then you have a local min when you change from decreasing to increasing, and that does occur at 5 pi over 4. So you do have one local minimum. Take both of those values and plug them into the original function so you can get the y values here. So if I start with pi over 4, sine of pi over 4 plus cosine pi over 4, both of those are equal to root 2 over 2 plus root 2 over 2, which is 2 root 2 over 2, which is root 2. So you get a value of root 2. And then just to save a little bit of time, if you plug 5 pi over 4 into the original here, you're just going to get the negative values instead. So you should end up very similarly getting negative square root of 2. So you have one local maximum and one local minimum on this interval. So that takes care of all the first derivative stuff. Now we're going to do the exact same thing for the second derivative. So now in red, we're going to find f double prime of x. So go back to the green box here and take the derivative again. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine, and we're going to set that equal to 0 again. It doesn't matter which one you move over, just to keep it similar, I'm going to move the sine over again. So this is negative cosine of x equals positive sine of x. And if I divide by cosine again, this time it leaves you with a negative 1 on the left, but you still get a tangent of x on the right. So it's just the other two angles we didn't use. Tangent's negative in quadrant 2 and quadrant 4. So that's going to be at 3 pi over 4 and 7 pi over 4. I'm going to draw my new number line. This time I'm going to use the second derivative. So we've got 3 pi over 4 and 7 pi over 4. But the good thing about these particular numbers is that I can actually use the exact same three test values that I used on the last part. But remember, this time you need to plug them into the second derivative. So if I plug 0 in, it looks like you should get a negative 1 as your answer, so that's negative. If you plug pi into the second derivative, you should get a positive 1, so that's positive. And since 0 and 2 pi are essentially the same thing, you should get the same answer, which is also negative. Now you can answer your next part. Interval of concave up, I'm going to abbreviate that CU to save some writing. So concave up only occurs in the middle, so that is 3 pi over 4 to 7 pi over 4. And then concave down is on each outer side. Remember, you have your interval at the top you have to follow. So that's only going to be from 0 to 3 pi over 4, union from 7 pi over 4, and you must stop at 2 pi. So there's your interval of concave up and concave down. And then just up here at the top, since both of those numbers change from either concave up to concave down or vice versa, they both have to be inflection points. So at 3 pi over 4 and at 7 pi over 4, you should have inflection points. To get the y value of those points, plug both of those numbers back into the original function. So if you plug 3 pi over 4, and this is actually going to be the best part, you actually end up getting 0 on both of these when you plug them in the original function. So in this case, you've got two inflection points. You've got your interval of concave up, your interval of concave down, to go along with what we found with the first derivative. So you see, these problems can be very tedious when you're asked to find everything. You got to take your time, do all your first derivative stuff, and then go through and do all of your second derivative stuff from there. Very good. All right, so then to wrap up this first section for this video, just a couple of thinking questions, and then we'll move on to the next section. Suppose that your second derivative is continuous on the interval negative infinity to infinity. If you know that the first derivative at 2 is 0 and the second derivative at 2 is negative 5, what can you say about the original function? So this is a way that I can check to see if you're understanding your definitions here. So first part, if you plug a number into the first derivative and it gives you 0, that means that x equals 2 is a critical number. That is the definition of that. And we learned earlier by the second derivative test is that if you plug your critical number into the second derivative, that tells you about the local max and min. So when I plugged 2 into the second derivative, it gave me negative 5. And when you get a negative number, this tells me that at x equals 2, you have a local maximum. Because remember, it works backwards when you do the second derivative test. So what does this tell us? That's all it tells you. It tells you that x equals 2 is not only a critical number, but it is also a local maximum. But what if I change it up a little bit? So be careful on part B. If the first derivative at 6 is 0 and the second derivative of 6 is 0, what can you say about the original function? Well, once again, f prime of 6 being 0 tells me that x equals 6 is once again a critical number. But unfortunately, when I plugged 6 into the second derivative, it also gave me 0. That tells me absolutely nothing. That number it equals has to either be negative and mean local max or positive and mean local min. If it equals 0, it doesn't tell you anything, and it just means that you need more information. There's not enough information here to make an educated answer for me. So that ends section 3.3. That's probably the longer part of this video because the problems take a little bit longer. What we're going to look at now is section 3.4, which is limits at infinity, and we're going to introduce the idea of a horizontal asymptote. All right, so earlier when we did limits in this class, we talked about how you can get an answer of infinity or negative infinity, and that meant you had vertical asymptotes. What we're going to look at now is what if you want to take the limit as x approaches either positive or negative infinity. So there's not a lot new here. If you want to pause the video and write all this down, you can, but essentially what we're going to do for the next little bit is I'm going to ask you to either take the limit as x approaches infinity of f of x, or take the limit as x approaches negative infinity of f of x and see if it's possible to get a limit value. Now, a lot of the times it's not going to work. But if you can find a limit value, and I picked out some problems in this section that we can do that in, that L value is now called the horizontal asymptote. So if you can find an infinite limit, which means your limit as x approaches positive or negative infinity, if it's possible to do, that finite number is going to be a horizontal asymptote. And it's written in the form y equals L. Now, one major difference to note about horizontal asymptotes, as you can see from the 3 pictures at the bottom, when we did vertical asymptotes, that is what made the limit infinity, which means that it blew up to infinity. You're not allowed to cross vertical asymptotes when you draw them. We haven't drawn any yet, but we'll see that in a little bit. But sometimes horizontal asymptotes you are able to cross. Now sometimes they won't, and a lot of the ones we look at don't. But as you can see on this last one, sometimes your little wave here could just be bounded around your line. But I'm not so much worried about the drawing. We're going to draw a few things going forward with horizontal asymptotes, but for the most part, I want to make sure you know how to find these infinite limits. So before we actually find some, let's just practice this from a graph like we did back in chapter 1. I've given you 6 questions here. I want you to find a range of limits that we've done before and limits that are new based on this graph, and then we're going to use all this information to answer part F of this question. So let's start with the 2 new parts, part A and part B. What is the limit as x approaches positive infinity, and what's the limit as x approaches negative infinity? Well, remember, infinity is going off in this direction. So what y value is your graph going towards as you shoot off? Well, if you look, this part of the graph is starting to follow along this line here. And let's see, if this is 0, 1, that's going to be 2. So we have an infinite limit of 2. Now, positive and negative infinity limits don't have to be the same thing, so kind of the same idea. What if you go off in the other direction? So as you can see, this part of the graph, what if you shoot off towards negative infinity? If you go down a spot, looks like that's going to occur at negative 1. Then we go back and do a little bit of a review of what we did back in chapter 1. So when you do things like the limit as x approaches 0. So when you're doing like 0 numbers, you have to look what's happening on the left and the right-hand side of 0. Well, if you look, both of these arrows are both shooting down towards an infinite number. So I can say that the limit as x approaches 0 is negative infinity. Then I ask about 2 from the left and 2 from the right, because the overall limit of 2 actually doesn't exist. But if you look at, let's say, 2 from the left is shooting down towards negative infinity, versus 2 from the right is shooting up towards positive infinity. Now, while finding the limits is not hard and not meant to be difficult from a graph, here's what it's telling us. And I'm going to change to red here so you can see. Part F, what are the equations of all of the asymptotes? So on part A and B, when you take an infinite limit and you get a finite number, that means that you have horizontal asymptotes at both of those numbers. So that would be y equals 2 and y equals -1. And if you remember back to chapter 1, if just the opposite occurs, if you take the limit at a certain number and you get infinity or negative infinity, that means you have vertical asymptotes. So that would be x equals 0, and it doesn't really matter whether you use the 2 from the left or 2 from the right, it all means the same thing. You get x equals 2. So as you can see, if I draw a little dotted line here, at x equals 0 and x equals 2, those are both vertical asymptotes. Your graph will not cross those, but you actually also have horizontal asymptote at y equals -1 and y equals 2, but your graph is allowed to cross those. There's no rules against that. All right, something you're going to need in a second. Actually, no, we're going to need this in a second. I'm trying to think of the problem we're going to do. Yeah, so occasionally there may be a problem or two. Actually, we don't need that. All right, so what I want to look at now is how do you take the infinite limit of functions without a graph? Now, here's the good thing is that there's not a lot of work in these. Now, some may require you to do some rearranging, but a lot of them do not. So what I'm going to show you here is over here on the right. I'm going to write out some stuff. When you are taking an infinite limit, this is how you can do these problems in about 15 seconds apiece. When you do an infinite limit, if the top power is larger than the bottom power, that means that your answer is going to be infinity. Or I guess if you were doing a negative infinity limit, it could be negative infinity. It all depends on what limit you're doing in this case. So there's case number 1. If the top power is bigger than the bottom power, one of these two answers will be your choice. On part 2, what if the opposite happens? What if the top power is less than the bottom power? Or AKA the power on the bottom is larger than the power on top. That's the best case scenario. It's probably the least amount of work. Automatically, your answer is 0 because there is no such thing as plus or minus 0, so you're only going to have 0 as an answer. And then the one you got to pay attention to, and the one you're going to see probably the most today, is what happens when the top power equals the bottom power. If that happens, you're going to actually have what we call the ratio of coefficients. And now while that can be a little bit confusing, that's why my first example here is going to be case 3, so I can show you that. So look at example number 2 here. What is the limit as t approaches infinity of the square root of t plus t squared over 2t minus t squared? So look at the top and the bottom. Find your highest powers. You have a t squared on top, and you have a negative t squared on the bottom. Those are both the highest powers. They are equal to each other. So when they are equal, you look at the constants right in front. There is an understood 1 in front of this t squared, and this is an understood -1, and the ratio means you're going to divide them. You're going to take the positive 1, divide it by -1, and your answer is -1. That's your answer. That's all it requires to do infinite limits. Now they need to be in this form. If they're not in this form, we may have to rearrange some things, and we'll talk about that, but that is how you apply infinite limits to functions. Let's look at a second example of this kind. Find the limit or show that it does not exist for the infinite limit of x squared over the square root of x to the 4th plus 1. Now the first thing, once again, you want to do when you're doing these is find your highest power. On the bottom, it looks like it's an x to the 4th, and on the bottom, on the top, it is an x squared. Now I said on the bottom it looks like an x to the 4th, but note, where is that x to the 4th at? that x to the fourth is inside of a square root, and you cannot just ignore the roots on the bottom. So while the 1 doesn't play a big factor because it's not that big, it's not your highest power, the x to the fourth does. But since that x to the fourth is inside of a square root, you have to apply that property, and the square root of x to the fourth is x squared. It's not plus or minus, you're not solving an equation, you're just simplifying a radical. Now, instead of using this x to the fourth, I'm actually going to use this x squared. So that's case 3. Look at the ratio of coefficients. You have a 1 on top and a 1 on the bottom. So as you can easily see, 1 divided by 1 is 1. That is your infinite limit. So here's our first tricky one. Find the limit or show that it does not exist. And what you're going to think is, oh, it's not a fraction. I can just plug my numbers in. Well, that's where a problem occurs. So let me show you what happens if you try to plug your numbers in. If you plug infinity into this, you're going to get the square root of, let's see, all these become infinities, plus infinity, minus infinity. So initially you may think that, oh, this is infinity minus infinity, which is 0. That is a big fat no. That is not possible. You are not allowed to do this step because not every level of infinity is the same thing. So when you run into something like that, you're going to have to fix it. So on this particular problem, here's what you have to do. We are going to write this as the limit as x goes to infinity. We're going to leave the whole problem alone. But you're going to need to put this into a fraction form, that way that it can be simplified. So if I divide all of this by 1, then if you go all the way back to the limit stuff we did a long time ago, back in chapter 1, you can multiply the top and the bottom by the conjugate. So that is 9x squared plus x with a plus 3 over the same thing. When you multiply this together, it does give you the limit as x approaches infinity. So remember your trick about conjugates. You only have to do the first and the last. So if you multiply the first, that's the radicals. That's 9x squared plus x. And then multiply the last. Oops, I forgot my x's. I apologize, y'all. I just totally forgot the x's. Don't do that. You'll mess up. So you should get negative 3x times positive 3x is minus 9x squared all over, and then the bottom doesn't change. It's the square root of 9x squared plus x plus 3x, because multiplying it by 1 doesn't do anything. As you can see on top, your 9x squareds cancel, and you're left with your new problem. The good thing is that it's now in fraction form. So find the highest power on top and bottom. Well, the only power on top is this x, so I'll box it in. Your highest power on the bottom, here's where it's tricky. You see that this 9x squared looks like the highest, but you see that it is inside of a square root. So I can say that the square root of 9x squared is 3x. But that means it now matches the other 3x that you already have out there. So you can't just ignore this. You now have to put these together because essentially they are the same power. That's going to give you a 6x. So in the end, your largest power on the bottom is a 6x. So just kind of be careful. It's a little bit tricky there. They match again. So use the ratios. You have an understood 1 on top. You have an obvious 6 given to you on the bottom. So your final answer here is 1/6. A lot of people put 0 on this one, or a lot of people put 1/3. People forget that when you simplify that square root and you pick up a 3x, you now have to combine it with your other x term that you have in the problem. All right, so while infinite limits are great, essentially what's a little bit easier, and what the whole point of this is, now we got to be able to find all of our asymptotes, and that's what I really want you to be able to do, because this is kind of the last little, what I'll call grooming technique to get you ready for the problem we're going to graph in the next video. So given this function, can you find all of the horizontal and vertical asymptotes for each curve? So you'll notice that I always start off with the horizontal asymptote, because based on what we just talked about, you're being asked to take the limit as x goes to infinity of the original function. But you are allowed, as I showed y'all, to use your shortcuts. Use your highest power on top and bottom. You have a 2x squared on top. You have a 1x squared on the bottom. Since they are the same, you can match their ratios and divide them. So that means normally you would write an answer of 2, but since the homework's going to actually want the asymptotes on this problem, horizontal asymptotes always use y. So your only horizontal asymptote is y equals 2. For vertical asymptotes, this one you actually need to go back to chapter 1 when we did this, and remember this means you need to simplify. So the question is, can we factor the top and the bottom? So let's check the top. Is it possible to factor that function? Let's see, 2x and x, 1 and 1. It is. It should factor into 2x minus 1 times x plus 1. And then if you factor the bottom, it should factor into x plus 2 times x minus 1. Now you'll notice the next thing you're supposed to do is cancel off any like terms, but there are no like terms. That's fantastic. If nothing cancels, nothing cancels. To find your final answers, you take just your terms in the denominator and set those equal to 0. So that would be x plus 2 equals 0 and x minus 1 equals 0. If you solve both of those, you get x equals negative 2 and x equals positive 1. So in this example, you've got one horizontal asymptote and two vertical asymptotes. All right, so let's do that again. What about if you have y equals 1 plus x to the 4th over x squared minus x to the 4th? So same order again. For my horizontal asymptote, I'm going to take the limit as x goes to infinity of 1 plus x to the 4th over x squared minus x to the 4th. I'm going to look for the highest power, so you have a 1x to the 4th on top, a negative x to the 4th on the bottom. So if you divide the constants, 1 divided by negative 1 is negative 1, but you got to put it in horizontal asymptote form, so that would be y equals negative 1. For vertical asymptote, you need to factor the top and bottom if you can. Now 1 plus x to the 4th, you're not going to be able to factor, so I'm going to leave it alone. On the bottom, they both share an x squared in common, so I can factor that out and make it x squared times 1 minus x squared. But once again, nothing ends up canceling here, and that's perfectly fine. If that's true, just take the bottom of your new fraction and set all of your terms equal to 0. So x squared equals 0, and 1 minus x squared equals 0. On the first one, if you take the square root of both sides, you're supposed to get plus or minus, but there's no such thing as that in 0, so you get just x equals 0. The second one, I'm actually going to move the x squared over to the right and make this 1 equals x squared, and then here's where the plus and minus comes into play. If you take the square root of both sides, the square root of 1 is actually plus or minus 1. So in this example, while you only have one horizontal asymptote, you actually have 3 vertical asymptotes in this problem. So very good. All right, so I haven't showed you one where it actually simplifies, and also I'm going to show you a different infinite limit we haven't seen yet. So once again, can you find the horizontal and vertical asymptotes for each curve? What if we have y equals x squared minus 1 over x cubed minus x squared? One more time, at least on this problem, the horizontal asymptote is the definition of the limit as x approaches infinity of x squared minus 1 over x cubed minus x squared. And you'll notice, don't just jump to the x squareds. The definition is look at your highest powers. While that is an x squared on top, your highest power on the bottom is actually an x cubed. That's case number 2 that I went over earlier with y'all. If the power on the bottom is larger than the power on top, your answer is automatically 0. And if you put it into horizontal asymptote form, that would be y equals 0. For vertical asymptote, you're still going to factor everything, so factor the top and the bottom. The top is actually a difference of squares, so that factors into x plus 1 times x minus 1. And on the bottom, you're going to factor out your common x squared, which leaves you with an x minus 1 left over. And as you can see, as a reminder, when there is a common term, you need to cancel that out, which leaves you with a simplified x plus 1 over x squared, but for vertical asymptote, you only set the bottom part equal to 0. So x squared equals 0, take the square root of both sides, and in this example, you have one horizontal asymptote and one vertical asymptote. All right, and last but not least, I want to kind of get you ready for graphing in the next video. So the next section, while not a long section, we're not going to do a lot of it, that you have to be able to graph basic functions using derivatives and different things. While we're not going to do any derivatives on this problem, I want to kind of show you the idea because asymptotes do play a role. The example says, can you find the intercepts and the asymptotes? Use them along with a few additional points to sketch the basic curve. So let's start with what we've been doing for the last little bit. Let's start with, at the top, horizontal asymptote. That's going to be the limit as x goes to infinity of x minus 1 over x plus 2. Since the top and the bottom both match again, you use the numbers in front, which are both 1s, and we can say that we have a horizontal asymptote of y equals 1. For the vertical asymptote, you need to factor. So in this case, though, you're going to notice that neither the top nor the bottom is going to factor in this case. You don't have to worry about that. All right. So if you set just the bottom equal to 0, you can say that x plus 2 equals 0, and therefore x equals negative 2 is your vertical asymptote. We found them. We'll come back in a minute and we'll sketch them together on our graph. Next thing it asks us is for intercepts, so I'm going to do that part in red. When you find an x-intercept, that is the definition from algebra of y equals 0. So if I let y be 0 in my original problem, that is 0 equals x minus 1 over x plus 2. I'm going to actually multiply everything, because I want to get rid of the fraction here. Let's multiply everything by x plus 2. Now multiplying it by 0 doesn't do anything, so you still get 0, but you do cancel them on the right, which gives you an x minus 1. Add 1 to both sides. That means that you have an x-intercept at x equals 1. All right, then you've got to do the y-intercept, which has a definition of x equals 0. So that would be y equals 0 minus 1 over 0 plus 2, which does simplify into a negative 1/2. So in this case, you do have one y-intercept and you do have one x-intercept in this problem. So in the end, your goal is to graph this. So I'm going to graph really quick just what I found so far. Y equals 1. So if I go to 1 on the y-axis, according to my asymptote, I have a horizontal asymptote at that point. If I go to negative 2, I have a vertical asymptote. So we'll take care of those. If I go to the x-axis and go to 1, you should have an x-intercept, so I'll put a dot there. Versus the y-axis, if I go to negative 1/2, I will also have that. Now, I mentioned earlier, you're not allowed to cross vertical asymptotes, which we're not going to do. You can cross horizontal asymptotes, but for the most part, the ones that I'm going to pick out for you, unless I tell you otherwise, we're not going to cross. So what you can tell kind of over here is that, well, I know I have to go from this point to this point, but as I go from this point to this point, since I cannot cross any of these asymptotes, at least not right now, I'm kind of forced to fit this mold just kind of based on the idea. We can't curve it up any other direction because if we do, it's going to try to cross the axis and that's going to be wrong. But is this the only spot where this exists? What about on the other side of this vertical asymptote? So while that vertical asymptote is at -2, what I would recommend you do is pick a couple other points on the other side of -2. Let's say -3 and -4. Plug those into the original function and let's create some points. So I know I have -3 something, -4 something. If you plug -3 into the original function, let's see, -3 minus 1 is -4, and then over -1, so that's going to be +4. So if I go to -3, 2, 3, 4, it's going to be about right there. And if I plug -4 in, that's going to be -5 over -2, which is 5/2. That's about 2.5. So if I go out to -4 and then go up to about 2.5, you could plot a few more, but you're going to see a very similar shape start to develop. Since we're not going to cross these asymptotes, in this case, you have approximately this basic sketch. Now, while that may not be perfect, that kind of gives you the idea is that while calculus does play a big role, and we're going to see that in the next video, sometimes things as simple as plotting points can give you an idea of what the basic sketch of a graph looks like. That ends this video on sections 3.3 and 3.4. We have one more video to go, so the next video will be the last one. It will cover section 3.5, which is more graphing stuff, and then 3.7 and 3.9 are a little bit different sections, but we'll do those in the next video.